Here the first component is 1, second component is 3, third component is 4. So whatever these ordered triples are doing, or whatever they are, can be completely characterized by these functions. And conversely, if you look at this, you can clearly see what function they are coming from. So practically speaking, in practice, there is no difference between this ordered triple and this function, and this difference in particular is not there at all if instead of an ordered triple like this, you consider an infinite sequence which may be treated as an ordered infinity triple, or more commonly which is known as a sequence of real numbers. Do you remember the definition of a sequence of real numbers? If you have got those things, it is defined as a function from the set of natural numbers onto the set of real numbers. Okay, so in that sense, these are actually nothing but finite sequences. So what is the advantage of not thinking of this Cartesian product like this, what we usually do, and thinking of them as functions? The advantage is that the power set axiom allows you to say that this collection of all functions is a set. Then using the axiom of specification, you can, from that set of functions, you can collect those functions that in particular satisfy these axioms. Ultimately, whatever you get is this Cartesian product, although you have to, albeit you have to identify the functions with ordered triples in this case, in general with ordered n-tuple. The thing we have achieved here is that we have made sure, using only the axioms we have got so far, power set axiom and axiom of specification, that the Cartesian product is actually a set. Okay, so that's why we went like this, and we have no need to introduce a new axiom that tells us that Cartesian products are sets, legitimate sets. Okay, so after this, there are some small things that we need to say about this whole thing. And one more advantage of this type of thinking is that you can generalize this. We can generalize this to the Cartesian product of infinitely many sets, for which we actually have to wait for a long time, because this is available in chapter 8. We are now in chapter 3. See definition. (8) 4.1, that too in 4th section. There are some more things that I should perhaps mention. Note that when all the sets in an n-tuple of sets are equal to a single set X, that is, if xi is equal to X for all I lying between 1 and n, we denote the Cartesian product by this. Okay, and this notation you can make sense of this notation like this also. You see, if you are thinking of this Cartesian product like this as a set of functions, what happens in this particular case where x is all the xi's are equal to x, you are going to consider the set of all functions from this set of natural numbers lying between 1 and n into the union of all the xi's. But here all the xi's are equal to x, so the union is x itself. And then what you are going to do, then from that set, you are from which set? From this set. From this set of all functions from this into this, you are going to collect those functions which map I onto an element that belongs to xi. But here all the xi's are equal to x, and hence that is anyway true. You see, you take any function in this set, that function will map I onto something that must belong to xi if it has to belong to the Cartesian product, and that xi is x. Since after all we are considering functions from this into x, the ith component will belong to xi because all xi's are equal to x. So using the axiom of power set we get this set, and then using the axiom of specification we don't get a proper subset that is really proper, but we get the set itself, that is, this itself is the Cartesian product. That instead of denoting the set like this, we denote it like this. You know why? Because there are n elements here, so we write n above. So the notation that we have fixed for, say, the set of all functions with z as domain and x as range, that reduces to this notation. Okay, instead of writing the set itself as an exponent, we write its cardinality. So I think you can understand how this notation and this notation are linked. So that's why when you write Rn, n-dimensional Euclidean space, although you are considering vectors with n components, but they are also sequences whose domains are equal to this, and they will tell you, that function sequence will tell you what is the first term, what is the second term, etc. And that you can also write like this as a vector with n components, that tells you what is the first term, what is the second term. So there is no real distinction between a vector and a finite sequence. That's what I am saying. Okay. Now in this special case, there are yet some more special cases depending on the value of n. If n is equal to 0, then we have already seen that the Cartesian product has only 0 tuples. Now since there is only one 0 tuple, okay, just like there is only one empty set, there is only one 0 tuple, then this is not the empty set but the singleton set. Consisting of the 0 tuple, and that 0 tuple is sometimes written like this: there is nothing inside, no component. Okay, if n is equal to 1, then x1 is the set of all 1 tuples x where x belonging to x. In practice, there we do not distinguish between an element and the 1 tuple formed by that element. Okay, there is, we can do that. For example, R1, we treat it as a line. We also sometimes, instead of writing 1, we write it as R. Strictly speaking, they are two different things. This is a 1 tuple of real number where there is only one component, first component, and that is R, and the real number R itself. We do not distinguish between them. That's why we write equality like this. We treat this as set of vectors with only one component, but we identify that vector with the sole scalar component that it has. So with this identification, the set of R, although x and this x are strictly speaking different objects, we do not distinguish between them. Now, if we are not distinguishing between an object and its corresponding 1 tuple, so clearly we are not distinguishing between the set X and this Cartesian product. That means we are identifying them to be the same thing. With this identification, we then have x1 equal to x. Okay. Right. Now we look at another example which will illustrate yet another point about Cartesian products. Example 359. Let A1 comma B1, A2 B2, A3 and B3 be some objects. Let x1 be equal to A1 comma B1, x2 be A2 comma B2, and x3 be A3 comma B3. We are now going to form some Cartesian products of these three sets, but not, we are going to form all the possible Cartesian products, keeping the order fixed. First comes x1, then x2, then x3. Then what is x1 cross x2 cross x3, just like that. So it will consist of ordered triples. The first coordinate can be A1 or B1. So let us first work with A1, and the second and third coordinates have to come from x2 and x3 respectively. So A1, A2, A3. A1, A2, B3, A1, B2, A3, A1, B2, B3, and then the same thing, similar thing with B1 in place of A1. So B1, A2, A3, B1, A2, B3, B1, B2, A3, and finally B1, B2, B3. So this is the Cartesian product x1 cross x2 cross x3. But we will calculate another one. This one, however, is different. It's not directly a Cartesian product of three sets. First we have taken this Cartesian product, and then with this set we have taken the Cartesian product of x3. So it is slightly different. Elements in this are not ordered triples. They are ultimately going to be ordered pairs, but the first coordinates themselves will be ordered pairs. If you really think about it carefully, an element will look like this: A1, A2, A3. This is an ordered pair where the first coordinate itself is an ordered pair. There is no, nothing says that that cannot be done. We just want the components in an ordered pair to be some sort of objects. So they themselves may be ordered pairs. Then A1, A2, B3, A1, B2, A3, B1, A1. Oh no, sorry, I cannot put A1, A2. B1, B2, A3, and finally B1, B2, B3. And like that we can also form this Cartesian product. So this will consist of these elements A1, A2, A3. Now the second coordinates of the ordered pairs will themselves be ordered pairs. A2, B3, A1, B2, A3, A1, B2, B3, B1, A2, A3, B1, A2, B3, B1, B2, A3, and finally B1, B2, B3. You can see that all these three sets are actually mutually disjoint. First of all, the elements in the first set are ordered triples, whereas those in the second and third set are all ordered pairs. So there is no question of having common elements. In the second and third sets, however, although the elements are ordered pairs, but in the second set the ordered pairs have their first coordinates or first component themselves as ordered pairs, which is not necessarily the case here. And also you can see that none of the elements are, no element in one set is there in any of the other two sets. So they are mutually disjoint. Strictly speaking, all the three sets above are distinct. But in practice we do not bother about this distinction, and we treat them as if they are the same thing. We do not distinguish among these differences. So, if we have a function whose domain is, say, this Cartesian product, here you have to understand that by this Cartesian product we do not necessarily mean the set of ordered triples, although that's what we said in the definition of a Cartesian product. We said that if there are three sets involved, the elements in it will be ordered triples. But in this context of being a domain of a function, sometimes you already know, or we have already seen, that we can think of things in terms of one variable or two variables, in this case three variables. So if we have a function, then we can view f as a function of one variable this belonging to the domain or as a function of two variables x1, that too can be done in two different ways, x1 belonging to x1 and x2 comma x3 belonging to this, or as a function of three variables. Okay, so that can be done. We shall not distinguish among these different perspectives. And then comes the remark which says that ordered n-tuples can be viewed as, actually not can be viewed, but they are truly finite sequences. So this is the 10th remark, I believe. Not 10th remark strictly speaking, but the 10th item in this section, which happens to be a remark. An ordered n-tuple of objects is also called a finite sequence of n terms. Okay, they are called finite sequences, and as such they are by definition functions. So you can see that we actually these n tuples, although they have been defined like they are some new sort of object or vector, truly speaking they are just functions. So there is no problem in treating a Cartesian product as a set of functions, because actually that's what they are, finite sequence of n terms. And in chapter 5 we shall introduce the very important concept of infinite sequences. Construction of real number system from the system of rational numbers will heavily depend on this concept of sequences, and also they will appear again and again in many places in analysis. So infinite sequences are really the heart of analysis. Oh, there is example 3, 5, 11 also, but I think the contents of this example I have already mentioned. What this example says are just these things, that is, if all the sets in a Cartesian product are equal, then the product is denoted like this, and then the discussion on one tuple, empty tuple, those things that I have already mentioned. So this part has already been done. Okay, or let me just write, we have already made the remark before, not as this example made the, okay, it's not remark, or let me write it like this, we have already seen the contents of this example before, right? Okay, now comes the only result, lemma. I have already said about this lemma, and we have also made use of this. It is known as it has a name, it's called finite choice. It says that if we are given finitely many non-empty sets, then we can choose one element from each one of them. It's a part of the axiom of choice. But unlike the axiom of choice, this finite choice lemma is a result, is a consequence of the other axioms of set theory. But axiom of choice cannot be proved from the other axioms of set theory, and neither can it be disproved. So it's an extra axiom that we need to make set theory somewhat more tractable. Although as far as analysis is concerned, in many places we will not need this axiom at all, only sometimes we need the axiom. We will see more about this axiom in chapter 8, I think, where we come back to set theory once again. So let us now see what finite choice says and how to prove it.